Welcome to The Explainer. Today, we are taking a really fascinating journey into how things break, how they manage to stay standing, and the invisible forces working inside them. We're going to completely shatter the illusion of perfectly solid objects, because, well, in the real world, absolutely nothing is perfectly rigid.
Okay, here is our roadmap for today. 1. The myth of rigid bodies. 2. Stress, strain, and hook. 3. Beams, bending, and inertia. 4. How engineers learn mechanics. 5. Computational scaling and FEM. And finally, 6. The future of structural design.
All right, let's jump straight into Section 1, the myth of rigid bodies.
So let's start by challenging what you might think you already know about the physical world. What actually happens when the assumption of rigid bodies fails? I mean, in classical physics, it's really easy to pretend that forces just act on structures without causing any physical change to their shape. But in reality, absolutely nothing is perfectly rigid. Every single thing bends, stretches, or compresses under a load. And when that assumption of rigidity fails, things break.
And honestly, this brilliantly illustrates the fundamental shift from classical statics to the mechanics of materials. Statics deals with these idealized, rigid systems, treating forces like simple arrows on unyielding shapes. But mechanics and materials, it essentially opens up the object. It evaluates the internal realities, the stress, the strain, and the actual physical deformation. This transition to a mathematically rigorous science was heavily pioneered by Stephen P. Timoshenko back in the early 20th century, and his textbooks literally shifted engineering design away from purely empirical guesswork and toward precise analytical methods.
Moving right along to Section 2, stress, strain, and hook.
Now let's zoom in to the microscopic level and equip ourselves with a fundamental mathematical toolkit that engineers use to actually measure this physical deformation. The absolute crucial point here is cleanly separating these two concepts, stress and strain. Stress is the intensity of the internal forces acting within a body. You can think of it as the internal force pushing or pulling per unit area. Strain, on the other hand, is the physical change or fractional distortion that results from that stress. Simply put, stress is the invisible internal cause, and strain, that is the physical measurable effect.
Modern engineering relies heavily on this fundamental triad to predict structural compliance and ultimately prevent catastrophic failure. First up, we have kinematics, which maps out the geometric deformations, translating displacements into strain fields without even worrying about the forces quite yet. Second is equilibrium, which is the balancing act requiring internal stresses to safely handle all the external loads. And third, constitutive relations, which mathematically links stress and strain based on the specific physical properties of whatever material is being used.
Now, what's really interesting here is how we progress from a simple 1D approximation, where stress just equals a constant times strain, to a full 3D reality, using these four interrelated elastic constants for isotropic materials. Young's modulus is basically your resistance to being pulled. The shear modulus is resistance to sliding. The bulk modulus resists hydrostatic compression. And Poisson's ratio? Well, think about stretching a rubber band. You know how as it gets longer, it gets thinner in the middle? That transverse contraction is exactly what the Poisson effect is. And because these properties are mathematically linked, knowing just two of them allows engineers to fully define a material's elastic behavior. It's like a giant puzzle coming together.
Okay, Section 3, beams, bending, and inertia.
Let's zoom out a bit to structural components and see how these internal stresses affect everyday things, like the beams holding up the buildings we're sitting in right now. If you've ever wondered why construction steel is shaped the way it is, look no further than the parallel axis theorem. This principle dictates that placing material further away from a shape's neutral center axis exponentially increases its overall moment of inertia, which is just a fancy engineering term for its resistance to bending. This theorem is exactly why I-beams look the way they do. By putting the heavy material, the flanges, as far from the center as possible, engineers neutralize bending stress without adding unnecessary, heavy solid steel to the core. It is just an incredibly elegant mathematical optimization of weight and strength.
Next up, Section 4, how engineers learn mechanics.
So, with all these complex formulas and invisible forces, how do engineering students actually wrap their heads around this? I absolutely love this contrast. Elite institutions generally take one of two routes. They either lean heavily into rigorous math, or they get incredibly hands-on. At schools like UCLA and UC Berkeley, the progression is highly analytical, moving students from multivariable calculus straight into tensor-based stress transformations. But over at MIT, they do things a little differently. They use what they call guided discovery labs, where they literally have students twisting pool noodles, pulling finger traps, and bending Twizzlers. This bodily kinesthetic feedback helps students physically feel nonlinear deformation and torsional warping firsthand, right while they derive the complex differential equations.
But, for practicing professionals, eventually you have to leave the pool noodles behind. Understanding these concepts in the field means referencing standardized tables to translate raw theory into real-world applications. A structural engineer's library relies heavily on texts like Callister for choosing the right alloys, or Roerch's formulas to rapidly verify stresses in non-standard components. These references are the crucial bridge between academic theory and safe, functional industrial design.
And make no mistake, this is a high-stakes discipline. Just look at the professional licensing exam. On the Fundamentals of Engineering exam for mechanical engineers, mechanics of materials sits right alongside heavyweights like mathematics and dynamics, making up a solid 10% of the entire test. It proves that having a deep, verified understanding of how things deform isn't just academic, it is an absolute prerequisite to protecting public safety.
All right, Section 5, Computational Scaling and FEM.
So, what happens when structures become just way too complex for a human to calculate with a pencil and paper? Well, when engineering geometries get thick, classical simplifications actually become incredibly dangerous. For instance, thin-walled theory beautifully simplifies the math for analyzing pressure vessels by assuming a uniform hoop stress. But the moment that outer to inner radius ratio pushes past 1.10, that assumption completely falls apart. The stresses begin to vary drastically across the thickness of the wall.
13.9%. That is the exact discrepancy between a simplified thin wall calculation and the true thick wall Lemay formulation for a high-pressure cylinder. In structural engineering, a 13.9% underprediction of peak stress is literally a life-or-death difference. It proves exactly why advanced computational math is so critical when our analytical shortcuts hit their limit.
To handle these incredibly complex realities without spending decades on a single math problem, modern engineers use the finite element method, or FEM. By effectively dicing a complex 3D structure into thousands of tiny geometric blocks, creating a mesh, supercomputers can solve the local stress equations for each tiny piece and then stitch all the answers together. Today, engineers even automate these massive simulation pipelines using Python scripts, which allows for rapid design loops that can optimize structures for extreme conditions in just a fraction of the time.
Finally, Section 6, the future of structural design.
We've gone from atomic bonds to equations, and all the way up to supercomputers. So where is the mechanics of materials heading next? Well, the traditional line between materials science, which looks at microstructures, and solid mechanics, which looks at continuous stress fields, is totally dissolving right now. We are moving toward highly integrated multi-scale engineering, and naturally, this is paving the way for AI. Generative artificial intelligence and collaborative AI agents are stepping in to automate the entire design verification loop. They're identifying stress concentrations and verifying finite element calculations for next-generation aerospace alloys and flexible electronics faster than we ever thought possible.
So I want to leave you with this final provocative thought. The next time you walk across a massive suspension bridge or board an airplane, will you still see them as perfectly rigid solids, or are you ready to see the structures all around you as dynamic, deforming systems that are kept safely alive by a hidden mathematical reality? Thank you for exploring this fascinating world with me, and keep questioning the physics of the built environment all around you.